5.8, we're going to analyze graphs of polynomial functions using intercepts and other things. Should warn you, two of the examples in this lesson out of the three will require a graphing calculator. So we've had a lot of vocab last couple chapters, and I just wanted to take a chance to point out that all of these different sentences say the same thing. Zeros and factors and solutions and x-intercepts, those are kind of interchangeable words, interchangeable ideas. So take a look at that, make sure you're on the same page with me. So our first problem says graph this function. This is already factored, which should make you feel good on the inside. Because it's already factored, we can say, oh, the zeros are -3 and 2. And this one has a multiplicity of 2. So we can already put those in a graph. Before we do that, let's figure out some more stuff. Because this whole thing is an x and then an x squared, this whole thing is a cubic, which means the end behavior looks something like this. If you remember end behavior from earlier, if the degree is odd, you have an up and a down arrow, and then positive or negative leading coefficient tells you if you flip them or not. If I would have had an even degree, I would have had both arrows going up or both arrows going down. One more thing that might be handy to have in our graph is a y-intercept. To find a y-intercept, you plug 0 into the function. Maybe go ahead and pause and try doing that on your own, see if you get the same thing I do. In fact, we should make a table using some numbers. If you remember, the way we graphed before was like this. And the only new stuff since we used to make the table is now we know how to find x-intercepts. And really finding x-intercepts is the hardest part, except it's not too bad in this problem because we're already factored. Go ahead and pause the video, fill in the table, plot the points, and use the correct end behavior. See if you get the same thing I get. A couple things I'll point out that I think are places that you might make mistakes if you're not careful. One, some of you might have gone through this point down here instead of bouncing right there. That would have been bad because if you look at your graph, you'll notice you have an extra x-intercept. The only x-intercepts we should have are -3 and +2. If you have any other x-intercepts, you put something in the graph that doesn't belong. Other things I'll be looking for as I grade this is, do you have the arrows going in the right direction? And do you have the right number of bumps? Since this is a third degree, we should have 2 bumps. In fact, we're about to learn a vocab word for those bumps. It's a vocab word we've actually seen before. Anytime it's the top of a bump, you'd say this is a maximum. Bottom of a bump would be a minimum. Notice it's not the maximum of the entire graph, just the maximum in that little area. So we don't actually call them a maximum, we call them a local or relative max, or a local or relative minimum. We'll see that in the next slide. Local maximum happens at the top of a hill. Local minimum happens at the bottom of a valley. And this slide here tells you how many bumps you should have at the most. So next it says graph the function, identify the x-intercepts and the points where the local maximum and local minimums occur. We could try to do this by hand, but the intent for this problem is to practice with the graphing calculator. So go ahead and look at the graphing calculator supplement and see if you can come up with the same numbers I'm coming up with on this. And it turns out we have quite a few x-intercepts on part B, and we also have 2 minimums on part B. This last problem is also a graphing calculator problem, except you don't need a graphing calculator to set it up. What I want you to do once you pause this video is try to come up with the formula for volume. Hint, volume is length times width times height. And also try to come up with a good range of values for your x and your v that you would put into the graphing calculator to make everything fit nice. You should be able to come up with all that without the graphing calculator. I'll check in with you before you try putting it in the calculator. Okay, first up, we see that the volume is length, which is 20 inches minus the 2x's. The width is 16 inches minus the 2x's, and the height is x. What we also know is x can't be bigger than a certain number. X is really limited by that 16-inch side. If we made x any bigger than 8, we'd be cutting off more than we could possibly do in a physical situation. So we could either cut off 0 or 8. That's our biggest and smallest numbers. And if we did cut off 0 or 8, we'd end up having a volume of 0. Our biggest volume is a little harder to come up with. That you might have to play with the graphing calculator a little bit for. Let's go ahead and look at the supplement for the graphing calculator. See if you can come up with that value of x that maximizes volume. And it turns out this highest this graph goes is 420.1. So I decided to use 500 as my y max. That forces us to have 2.9-inch cuts with a total volume of 420.1 inches cubed. And that answers all our questions. How long should we make the cuts? What's the maximum value? And we still need to answer this guy. What are the dimensions? So then we just plug in our numbers. And we get something like so. And this is a great example of a real-world math problem where you've got physical constraints, but you want to maximize some number. In this case, we want to maximize how much space a box can have. At this point, you can pause the video and try these on your own, or you can do that later. Otherwise, we are done with this lesson.